I think there's a vending machine.
Wonderful answer, Christina. So, what did we test last time? Do you remember? Something. We did test something. It involved numbers. It involved three. Good. Very nice. Very nice. So, remember that? Beautiful. Beautiful. We had that little flow chart. Hypothesis testing, single parameters, double parameters. We're now, these last couple days, today and Tuesday, all I want to do is the multiple parameters. And I say multiple, 3, as Beth said, as Richard said, or more. So what we're in the middle of doing right now is how to test simultaneously 3 or more proportions. 3 or more proportions. That's the idea of today. And we'll see how time goes. I want to hint at 3 or more averages today, but we probably won't do that until Tuesday. And that's okay. That's okay, because I want to kind of let this guy fit in. And I heard Karen call it goodness of fit. I love that. It's called a goodness of fit test. And the formal name of the distribution is the chi-square goodness of fit test, chi-square. The reason the chi is squared, as you might remember from crunching the statistic manual, we had to square the difference of the observed and the expected in some point in the computation. And that square is a nod to that. The distribution, actually, if I had done more stuff in the beginning of the course, we would have experienced the chi-square earlier. But again, I tried that once years ago. And having the z distribution, the t distribution, and the chi-square all at once in the beginning was disastrous. Too much going on at once. Z versus t itself is a challenge enough. But having the chi-square that early, now the point is like, okay, I know z's and t's, I'm kind of happy with those. Now I can throw the chi-square and you're like, I got this. It's what you do when you have 3 proportions. So anyway, we got a program to run today too. Because that beautiful board that we filled yesterday with the computation of that test statistic was a little excessive. And when you have enough categories, it gets prohibitive. When you have 50 or 60 categories, it gets ridiculous. So let's review though, because I do want to bust the program out and show you how to use it. JD, you already on it yesterday when you said put it in L1 and L2. That was great. But let's revisit what we were actually testing yesterday. Do you remember what we were testing yesterday? What was the context of the experiment? Go ahead, Beth. Ashley helped out.
If the randomizer was working.
Right.
Oh, that's right.
Remember that? We were trying to see if the iPod randomizer is the iPod randomizer random. And when I say random, of course, I mean random enough.
Yeah.
I mean, it probably won't be. It's almost impossible for it to be perfectly uniformly distributed randomly. You guys figured that out very quickly, didn't you, Jerry? So, we had Ashley stand up there and shake the iPod 50 times, I believe. There are 10 songs loaded onto it. So excited, by the way. There's a new used vinyl shop in town. It's not really that new anymore. 4 months old. Recycle Music down at Bond in Arizona. Used vinyl. Recycle Music. I found, remember the Pat Benatar song on the mix? Yeah. Found the 45 yesterday with the color cover. Very excited. Not going to lie to you, 75 cents. What are you talking about, 75 cents? Couldn't be that cheap in the 80s.
No.
When it was new?
Yeah.
Hell. Anyway. Totally non-connected tangent. Great vinyl. Iron Maiden picture discs? Huh? Aces High picture disc, please. Clash outtakes. Yeah, I was a pig and poo. I'm not gonna lie to you. Anyway, you walk in there, you just walk in, you smell the body, you're like, oh yes, I'm home. Anyway, it is, but this is anyway. We'll talk at the break. So. How did we test whether or not the iPod was random or not? What were the hypotheses that we tested? Which one says the iPod is random enough? Which one says iPod? Absolutely, H not the null. It has to, because that's the one that says nothing is wrong all the time. Status quo. The iPod says it's random enough. There's no reason not to believe that. So yeah, this one here, I'll put it in words first. The iPod is random enough. That's in words. In symbols, if you want symbols, and you don't have to have symbols if you don't want them, but since we've gotten so used to seeing symbols, the program that I've written for you doesn't need symbols, just so you know. Just see, it doesn't need them. But if you need symbols, it just means all the proportions, whatever they are, are all the same. And they're all equal to 10%. Because if there are 10 songs on the iPod, you should hear every one 1/10 of the time, which would be 10%. If there were 20 songs on the iPod, you'd hear them 1/20th of the time, or 5%. If there were 100 songs on the iPod, 1/100th of the time were 0.01. So whatever, this is only for a uniform distribution. That's why I like the M&M experiment, because that's what happens when you don't have a uniform distribution, so you can see both sides of the coin there. Cool, so that's the null. So the alternative is definitely going to be the iPod is not random enough. I'll spell that. Yes, or no, I guess not random enough. Do you remember the way we phrased that? Go ahead, Richard, go, my friend.
The way we phrased
it, like if you want to use, without saying the iPod is not random, which is okay to say.
does not equal 1%.
Good. At least one of them
Yeah.
is significantly different from that 10%.
Yeah.
And there's many different ways you could write the alternative, many different ways. But the kicker is that at least one of them is far enough away from 10% to be like, there's something going on there. There's something going on there. And that's hard for us to judge. It's hard for us to judge by looking. Remember, at the very end of the day, you can say no on this one. This was just like 5 minutes to go at the end of the class. I opened up a spreadsheet, and I started F9ing random songs, and there were some where you didn't see any songs at all. Like, there was like no Iron Maiden, which I know is a crime. There's no Iron Maiden, but the p-value is still very high, which means it's still random enough. And you think to yourself, wow, if you don't hear any songs at all, how can that be random enough? And then you realize, well, you're only expecting 50 songs, right? 50 plays is the bare minimum. So in that, you can get no songs and still be within the realm of randomness. It's just that that clump hasn't happened yet. The clump's going to happen somewhere else. Please, Beth.
Isn't the randomizer on an iPod, though, how often you play the songs when it's not on shuffle?
Hold that thought for 2 minutes. Hold that thought for 2 minutes.
So
I want to come back to that.
Just one quick question.
Go ahead.
Is, say you had never played any songs on your iPod, you
Okay.
just loaded them.
Okay.
And then you hit shuffle.
Mhm.
Then that would more be like a true random.
Hold that thought. Can you hold that thought?
I'll try my best.
You're asking a very good. I just want to get these hypotheses wrapped up before I come back to that, because what your question is, you're motivating the whole reason we're doing this experiment. Remember how we did the stopwatch, thumb versus finger? Why did we do that? What was the whole motivation of that experiment? You're right. Why? Go back even further.
Parents were complaining.
Because the parents at Bend High were complaining that some of their the whole point of these experiments, hopefully, whenever I can get real data in class, is because I'm interested in something that's happening. I read that iPod messed with the randomizer to make people happy, to make less clumping. So I'm trying to see if my iPod Touch has the same goof with randomizer that the iPod Shuffle did. So that's the motivation.
But,
Yeah.
But wouldn't it be like the clumping would be altered because you have
The beautiful part of this test is it allows for the clumping. It allows for variations in clumping. It almost as if, and I'm going to say this with quotes, it knows that the clumping is there, and it's allowing for clumping that's not there to be allowed for later on, because it almost like predicts that the clumping is going to happen. Does that kind of make sense-ish?
Yeah.
So it's in there. It's part of the test itself. That's why we can do it simultaneously. Fantastic. Now at this point, these are the beautiful hypotheses. Right? It's always good to have them because you know what you're testing against. Now the question is, what's the test stat and what's the p-value? And what I want to do, because this is where the videos got a little bit corrupted, for some reason the camera got goofed yesterday. I have no idea what happened still. But we're going to pull down, when we get these using the TI, we're going to pull Excel down, and we're going to take a look at the curve again so you can see exactly what that looks like. So we did these both, well, we did this one manually yesterday, and then we pulled the p-value again using technology. So let's grab your TIs, because I wrote you guys a program that does this so you don't have to do it manually. Only because the old 83s don't have this at all in them. The newer 83s, the 84s, have a built-in, but I think mine's a little bit more user-friendly. So let's fire these bad boys up. Make sure you can see this. Yes. Okay. So what you want to do is you want to go to you want to go to stat first. You have to put your data in before you run my program. So in edit, we have to put in the songs, occurrences that we saw. And I don't think I kept them from yesterday. I didn't. Does anybody have the songs written down? You got them, Christian?
Yeah.
So just get in L1, give me the occurrences that we saw. It doesn't matter what song is which. Just go down the list for me.
Okay, yep. So 5,
5,
4,
4,
5,
5,
4,
4,
9,
9,
3,
3,
4,
4,
3,
3,
8,
8,
5.
and 5. Okay, let's go through that again. Make sure everybody gets it. Make sure everybody gets it. So clear out L1. We saw 5 of whoever 5 was. Then we saw 4. Then 5, 4. So 5, 4, 5, 4. 9. That's the first 5 songs, occurrences. So the 9 was the spike. I think Pat Benatar, if I remember correctly, or something like that.
No, that was Queen.
Queen, that's right. Too much Queen and too much social distortion. That's right. As if. And then 3, too little, whatever that was. Well, that was Billy Idol.
Yeah.
Oh. Did Generation X, 12-inch, third release from Generation X, Billy Idol's old punk band, on like half-pound black vinyl, $10. I mean, seriously, $10, really? Seriously, go to the shop. It's wonderful. Anyway, 3, 4, 3, 8, 5. That's what we saw. So I called that the observed column. O for observed. What goes in list 2?
All
5.
5s.
Why all 5s? Yes, Richard.
Expected.
Because we expected 5 of each in a perfectly behaving randomizer. It's 5 of each. 5, 5, 5, 5, 5, 5, 5, 5, 5, 5. And make sure you have the same number of 5s. Now, what we did next was a little bit convoluted. We took the difference in L3, then we squared the difference, then divided by E, and then summed it up. The TI will do all this for you now. That's why I wrote, it's a very short little program, but it does all this for you. So, got your data in? Go program. I couldn't put it in the stat menu, so it's under program. Find one that says Goff. I gave this to you guys back in 243 with a promise that we'd eventually use it, and here we are finally, using the 5th program I gave you. So Goff, grab it, start it up. It asks where your observed list is, just tell it L1, so second 1. It asks you for your expected list, second 2. Press enter. It presents you with your test statistic, which we got, remember yesterday, 7.2, right? 7.2. With the variable, chi-square. 7.2, beautiful. And it gives you your p-value, about 62%. Well, you're good. That's why I write these. I mean, that's the whole reason we have computers, is to do lots of computations for us. Please, Christian.
And this is 2 questions review.
No, it's not.
This is testing H1.
Yeah, well, we always are testing H1, essentially. We're trying to see if we're far enough away from this guy to get to this guy.
Okay.
So, first of all, I want to come back to that. Give me 2 minutes if you don't mind, Christian, because it's a great review question.
Yes.
I want to come back to it. But first, I want to make sure we re-answer Zoe's awesome question from yesterday, what the 7.2 means. Because if you think about 7.2 as a test statistic, that seems very far away from average, because if you're thinking about a Z distribution or a T distribution, that's 7 standard deviations. That's ridiculous. But it doesn't mean exactly the same thing on the chi-square curve. That's why I want to pull down the screen here real quick and make sure you realize that 7.2 on a chi-square curve is actually hardly deviant at all. And I want you to make sure you can see that. Oops. Need it over here. Maybe it's a source problem. Computer? Maybe. Or not. Oh, there we go. There's the M&M chart. We don't need that one yet, assuming. Okay, so here's this beautiful chi-square chart that we looked at yesterday. I call it beautiful. You might just call it Thursday. That's fine, too. There's what our actual curve looks like. Remember, it's not symmetric. It's highly skewed. Highly skewed. As the number of categories goes up, it gets less skewed. But ours categories never go above, say, 20. So, what's the minimum value on the horizontal?
0.
Good. Do you remember why it's 0? Why there are no negative values?
Because we squared it.
When we squared the data, the observed minus expected, you erased any negative values. So any differences have to be at least 0 or positive. So if we ran the randomizer 50 times and got 5 of each of the songs, I would have passed out, just so you know. I would have passed out on the floor if that happened.
I'm certified for CPR.
Awesome, thank God. I will be tomorrow after tomorrow. But here's why I'm not worried about passing out. Because the chance of that happening is essentially 0. This is a nod to the fact that, yes, random means 10% over time, but it doesn't mean 10% right there in the beginning. Going back to what Beth asked about, again, very good question. So what happens is, as you get further away from 0, there's an allowable amount of deviation that happens. And that's where the bulk of the curve is. Where's our 7.2? Right about here. And if you form the p-value by shading all the curve over that way, you're shading a huge chunk of the curve. How much of the curve again? 62%. Right? You've got 2/3 of the curve shaded. So what does that tell us about the randomizer on the iPod?
It's random.
It sounds like it's working. Who do we believe?
Not.
We believe, good, that's actually, who do we believe? Not. That's exactly right. We believe this guy. A big p-value means the same now as it has meant at all times. It means we believe this guy. Christian, back to your question, which was awesome. A big p-value means exactly the same now as it has meant at all times that you believe this guy up here. If that came in under 5%, then I believe this guy. I believe something was up, some song was off. More on that, about 20 minutes or so. More on what happens when that happens, because I can almost guarantee we're going to get a small p-value with M&Ms. I can almost guarantee it. Beth, go ahead.
On the test, will you want us to say it does or does not appear?
Sure, just say, and this was, I know this was a bit of a point of consternation yesterday, because I said it appears that the randomizer is working.
Yeah.
And people were like, wait a minute, a big p-value means it does not appear. And I was like, oh, okay, so it doesn't appear that it's not working. And I think that pissed some people off. So so basically, when you say something does not appear, it does not appear that you've deviated from this. That's what the does not appear means. So this is where English gets in the way of mathematics a little bit. You have to be able to say this concisely, but there's more than one correct way of saying it concisely. One way of saying it is, it appears the randomizer is working, which basically means just agree with this. The other way is to say that, and this goes back to the whole fail to reject the null idea. You fail to reject the null, that means it doesn't appear that the randomizer is not working. And that's okay, you can say that if you want to. You don't have to say that. As long as you know this agrees with that, and that is implying that the randomizer is random enough, I'm a happy guy. Say it any way you want to. Go ahead, Jamie, ask me that question.
On the test, you don't have equal to, greater than, or less than there?
No!
Can you do that?
This is a great, can you give me 32.3 minutes?
Okay.
We'll come back to that. That's a great question. Do you hear Jamie's question? There's no less than, greater than, because think about why. Think about all the possible combinations. I mean, there's only one way for them all to be equal. What's 2 to the 10th power, friends? What's 2 to the 10th power? About 1,000-ish. That means there are about, I think it's 1,024, right? There is one way for them all to be equal. There is 1,023 ways for them not to be equal. You'd have to list them all out. Holy hell no. No. They're all wrapped up right here.
Okay.
So,
We can do that.
oh my God, yes. As a matter of fact, what I tend to do on this last exam is I leave a gap for these, but I don't require you to write them.
Okay.
I encourage you to. It keeps you track. But what I'm really interested in are these guys right here. And the conclusion. It appears or does not appear. The randomizer's working, the randomizer's not working. Does that make sense?
Yeah, I just wanted to.
Oh, no, very, very good, very, very good. I slapped a quiz up for next week, too, a Goff quiz. You'll see like kind of a format of a Goff problem for next Thursday. Yeah, Christian, go ahead.
So are you going to cover in more detail? What's that 7.2 mean?
Good. It's distance along this horizontal axis.
Okay.
Technically speaking, let me show you what it actually is equal to, Christian, over here with the TIs. If you go back to your stat editor, you'll now see that L3 is full of stuff. I wrote the program to clear L3 and replace it with, if you remember the board full of stuff we did on Tuesday, the last column, O minus E squared all over E, that's that column right there. So the 7.2 is the sum of all these values. Now those values themselves are a bit of a standardized deviation measure. They're not a standard deviation. That's what Zoe's question was so awesome on Tuesday. It's not the same thing as S or little sigma. It's a different kind of deviation measure. The bigger they are, the more deviant they are from expectation. And you can see 3.2 is the biggest one. Well, that's because 9 was the biggest deviant from 5. But as far as contextual, there's not much context to them. There's not like a unit attached to them. It's not like 3.2 songs or something like that. It's just, it's the chi-square deviation measure. So to speak, it's been set up to agree with this curve, if you will. So it is a deviation measure, and the more deviant, the less likely, obviously, I've passed the point. So if you're getting chi-square measures that are 60 and 65 and 70, you're like, wait a minute, something's going on. From zero. They're all measured from zero. Very, very good connection. Right, and you would expect some deviation from zero because of random clumping. If the randomizer goes, what are the reverses of 8, 9, 10? What are the reverses of 8, 9, 10? What are the reverses of 8, 9, 10? There's something's going wrong, right? You can predict what's going to happen next, which is the opposite of random. But this is pretty much front-loading the clumping idea. Karen, was that a question? Go ahead. Awesome
Yeah.
question,
So
Christian.
you said the number of categories we would have would never exceed 20?
In here,
in here.
theoretically, it could be anything you want.
So if you had a category that had 50,
Sure.
but your chi-squared was actually, say, 30,
Good.
then that would probably be far enough from 0
Check it
to
out.
possibly be suspect.
Check it out. Karen's
Oh,
got a very
nice.
good point. This is one of those interesting curves like the t-distribution. A chi-square test statistic of 7 doesn't always mean the same thing. It depends on how many categories you have. So as Karen just pointed out, suppose you had a chi-square of 30. On the last curve, 30 was highly suspect, right? It was
Yeah.
getting to the far side of that curve. Look at 30 on this curve.
Yeah. so almost
First of all, this thing almost looks like a bell, which is a function of that function. Not to use the word function twice. But it does tend to bell out as the categories go to infinity. But yeah, that deviation, that standardized deviation, it changes depending on the number of categories, and there's a reason for that. The reason for that is the more categories you have, the more deviation you're going to expect, especially on a small sample size. And there's a difference between the category size and the sample size. Does that make
Yeah.
sense? In other words, for the iPod, we had 10 songs, that was the categories. We shook it 50 times, that was the sample size. If we had 10 songs that we shook it 500 times, you're going to have a different result overall than we had most likely, because that clumping is going to start to smooth out at that point. So, great question. Very, very good formative mathematical question. Not so much statistical, but great mathematical question. But yeah, so all chi-square test stats are not created equally, is what we're getting at here.
Yeah.
And that's a very, very good point. Although, in general, bigger ones show more deviance than smaller ones, because they're getting, as Christian said, away from zero. Away from zero. Susie, go ahead.
So does the x-axis only equal to 100?
Does the x-axis...
How far does the x-axis?
Oh, infinitely. Very good question. How far does that x-axis, that chi-square axis go? It goes off forever. It stops at 0, but there is no top end. Because technically speaking, you can be infinitely variant. I mean, we could have shaken that iPod 50 times and gotten 50 Iron Maiden songs. Yes. We could have. We could have. It can happen, which would put us way the hell over down there. But it's just not likely. Just like on a bell curve. Bell curves go off infinitely both directions. It's just that it's very hard to get out of those tails. Cool? Good question. Good theoretical mathematical questions. Very, very good. Yeah? Jamie, go ahead.
I just want to clarify, you said it stops at 0?
It stops here. You can't go negative.
What,
No, it's
can
not.
you say
Look at this
it
end,
starts-
Jamie. It's over here.
Oh,
It's
sure.
down.
Okay, you're going right, I'm going left.
Okay.
I'm saying the curve coming, you're actually doing it correctly mathematically. It starts at 0 and goes forever that direction. I'm coming in from the right and saying it stops right here.
Okay.
Yeah, so potato,
I
potato.
thought,
No, you're right, totally right. Cool? Ish? Cool-ish.
On the final exam,
Yes.
are we circling like the last one, or we're writing out our...
You're gonna write the conclusions out. Yeah, and you guys are totally ready for this. You are, I can hear it. And the
How
thing
about
is,
the first exam, we were like, oh, it's at least, but at most, we were writing
exactly.
out.
You were
So
circling. Yeah, I had you circling for a while because I wanted you to get the flow of what the.
Right.
But now I think the flow is there, and that's what we're gonna spend the next couple of days doing is just verbalizing these
Right,
things and
yeah.
saying them over and over again.
All right.
Cool. Now I want to compare and contrast the M&M experiment with this one. Okay, let's put this up for a second. Just a sec. Mute the screen. So this is, I tend to break goodness of fit tests into two kinds. And they're both the same test. You run the same exact mathematics on both of them. But this one is where you're testing what I like to call a uniform distribution. And that's because all the songs are supposed to come up at the same frequency. 10%, 10%, 10%, 10%, 10%. And that's fine. But what if, for example, you're analyzing flu rates in the 6 counties of Oregon? Okay? What if you're analyzing flu rates? If you look historically at the 6, I say 6 counties, not 6 counties, the 6 regions, Northwest, Southwest, North Central, South Central, Northeast, Southeast. If you look at those 6 regions, which I have, and which you will do soon, the flu rates are not consistent. They're not the same in all 6 regions. You might think that they would be as a percentage, but they're not. They're higher in certain areas than others. And who knows why? There's many, many reasons as to why they could be. So in other words, the null hypothesis won't be that the percentage of one is the same as the percentage of none, is the same as the, it's that each percentage might be different. But you're still testing to see if you then collect data, say the next year, and see if it fits good enough, terrible English, I apologize, fits well enough with the distribution that you already had in place. And this is where M&Ms are the perfect way to motivate this. If you look at a bag of M&Ms, well, now actually I haven't heard the new data yet. I'm excited. We'll test it both ways once I get the new data. but I don't have that yet. If you look at, and I have to look this up because I never remember, a bag of milk chocolate M&Ms. Here we go. Here we go. Here we go. Here's the M&M experiment. Okay. It's still a goodness of fit test. Because how many colors are in a bag of M&Ms?
More than two.
More than, very good. 3 or more. There's 6 altogether. There's orange, yellow, brown, green, red, and blue. Back in the day, there were 5. There were 2 shades of brown, yellow, orange, and green. They've changed them over time since then. I found an old article from 1990 when they had a different percentage. I tested them both in the Excel spreadsheet. And they said that they did consumer tests, just like Ashley said, to see what color distribution is most appealing. And back in the day, people wanted mostly brown M&Ms. Maybe because brown correlated with the color, the chocolate, I guess, something like that, right? But brown has actually been there were 2 different colors of brown back then, light and dark. And now the tan's gone, and just brown is left. And there's great stories about bands like Van Halen when they were on tour. They would demand to make sure that people read their contracts. They put a line buried in like page 5 that said, as part of our rider, we want a bowl of M&Ms in each guy's dressing room with all the brown ones removed.